Okay, so we're going to work on chapter 11, which is called the chi-squared test for categorical data. So chi-squared test for categorical data. So we're still working with significance tests. And the big question is that, oh my gosh, we already have so many tests and intervals. Why do we need more? So why do we need more? Let's look at what we have. So right now we have a one sample Z significance test. So that does categorical data. But all we're really doing is we're looking at the proportion for one category. Then we have a 2 sample Z significance test, which analyzes the difference in proportions for one category. But what happens if we want to look at it for all categories? What if we want to analyze all categories? And that's when we get to the chi-squared test for categorical data. So in section 1, we're actually going to be looking at the chi-squared goodness of fit test. So let me talk about the Greek letter chi. It looks like a straight line, and then the other one kind of curves at the top and curves at the bottom. So it kind of looks like a fancy X, but it's really the Greek letter chi. This test takes one variable, so the variable may be favorite color, and it analyzes its distribution, so maybe like blues, greens, reds. So instead of looking at just one color, blues, so what proportion of the kids have blue as a favorite color? Then I'm not really looking at any of the other stuff. That would be our original Z significance test. But if I want to look at every breakdown in that favorite color variable, so every category that we determine, then we're going to use the chi-squared goodness of fit test. And so what it does is it compares the expected distribution to the actual sample distribution. And it tries to determine, is there really a difference in what we expect versus what we actually get? And so for this test, we compare counts, not proportions, which is different than any other significance test that we've done so far with categorical data. Usually when we're looking at Z's, we're looking at proportions. Now we're looking at actual numbers. Now our next ones are the chi-squared test for homogeneity and the chi-squared test for association or independence, depending on how you word it. Now these are the exact same test. What is different is how we get the data. So how we sample from our populations. So for homogeneity, what we do is we take 2 different samples. So we look at several populations, really taking 2 samples. So that may be that I'm going to go ahead and I'm going to ask only females, and that's my first sample, and then my second sample I'm asking only males. And so then I actually have 2 different samples that I'm looking at. If I look at chi-squared test for association or independence, this time we do a single sample. And when I go to a single sample, so I'm going to come up to someone and I'll be all like, okay, are you male or are you female? And then I ask them the question of interest. So the way I sample changes what type of test I'm working with. And so this one, I ask several questions and I break them up among the multiple variables. And then I see if there's an association, or if I check to see if they are not independent with those variables. And so the way I sample is the way I can tell what type of test I'm having. But everything else, the checking for conditions, the statistic, the way we calculate probability, that's all the same. So now we're going to go ahead and look at what is a chi-squared distribution. So we've done normal distributions, and then we've done t-distributions, which are just a little bit wider than the normal distributions, and it changes based on degrees of freedom. So a chi-squared distribution is a distribution that measures the distance, so this is really important, the distance of the observed count from the expected count. Now, unlike a normal distribution or a t-distribution, this distribution is not symmetrical. In fact, the chi-square distribution will change based on the number of categories, which will create a degrees of freedom. So when we're not going to be looking at the number in our sample anymore for degrees of freedom. We're going to be looking at categories for degrees of freedom. Now, as you could tell from our diagram, this is a chi-square distribution with a degree of freedom of 1. Looks kind of like an exponential decay. Now, here is our graph for a degree of freedom of 4. And then our graph for a degree of freedom of 8. And so what are we noticing? Well, we're noticing that it is definitely a right-skewed distribution. And then something else on why it's kind of right-skewed is that our values are always positive. So it never goes below this 0 line. So that's why we will tend to get a bunching of values around here. Now, as our degrees of freedom become larger, it becomes less skewed. So not as strong of a skew. And the degrees of freedom become larger, the larger values become more probable, which is then a higher p-value. Now, some characteristics of our chi-square distribution. The mode, or our peak, of the distribution will be at the degrees of freedom minus 2. So as we look at here, our degree of freedom is 1. We're going to have a peak at, well, kind of -1. But it's pretty much just going to go on up as far as we can. Now the mean will be same as the degrees of freedom. So here my mean is 1. Our average would be 1. Here our average would be 4. Here our average would be 8. And then the variance, which is really, variance is our standard deviation squared, is going to be 2 times your degrees of freedom. Now, how do we calculate the test statistic? Well, it is calculated by sigma, which is the summation of our observed information, so what we get from our sample, minus what we expect to get, squared, and we square it because we don't get a negative value, and then we divide by the expected value. Now this is found on your formula sheet, so you don't have to memorize this. But the more often that you do it, the more you just kind of know that it's OEE. So observed, expected, and then expected. Okay, conditions for any chi-squared test. So we have a random condition. So again, simple random samples or randomized experiments. And then instead of a normal, because it's definitely not a normal curve, we're just checking to see, do we have a large sample? And so when we have a large sample, we're looking to see that all expected values, not actual, so not what we get from our sample, what we expect to get needs to be greater than or equal to 5. So our expected counts must be listed, and we have to show every single category that those expected values must be greater than or equal to 5. And because we're going to be computing expected values, it's okay if they're decimals. In fact, a lot of times our expected values will be decimals. And then of course we have our normal independence condition, because that allows us to work with the idea of standard deviation and calculating our probability. Okay, so how do we do a chi-squared goodness of fit test? So we start with our state portion. We want to perform a chi-squared goodness of fit test, and a lot of times we write that as GOF, goodness of fit. And then we have to state a significance level. So it's important you do that at the very beginning. That has to be done. Typically it's done before you even collect data, but we're not working on collecting data, we're looking at analyzing that. So when we write all this stuff, this state stuff is all stuff that is typically done before you even collect data. Now our null hypothesis, or HO, is what the expected proportions are based on the population. And so typically we're going to list all of our expected proportions. Now our HA, our alternative hypothesis, is that at least one of our proportions is not going to match the population. So at least one of them is going to be incorrect. And then we have to make sure that we're stating, what does P stand for? This is the proportion of what? So like if I was doing the variable of favorite color, the proportion PB means proportion whose favorite color is blue. PR is the proportion whose favorite color is red, so on and so forth. Because we need to understand your notations as you're working stuff out. Then we move on to conditions. So random, we're checking to see if we have random sample or if we randomly assigned things to a treatment. Then large sample, we're going to check the expected counts, which means we're going to take the proportions from here and we're going to times by the total to get an expected count for each one. And then we're going to check for independence. Once we've done that, we're going to move on to calculating our values. So we're going to calculate chi-squared. And we're going to do that by taking, now we start looking at the observed data. So from our sample, how many did we get that whose favorite color was blue? And we're going to subtract the expected value, which we calculated up in here. And then we square that and divide by expected value. You have to list out at least first of the two terms. So if you have 20 different categories, we're not expecting you to write out all 20. But we do expect you to write out at least 2. So you can write this plus so on and so forth. And then tell us what the value is. Because we know you have a calculator, we need to make sure that you know how to set it up correctly. Once you have that chi-squared statistic, then we go to calculating our p-value. And p-values are our probability values, and we always use our CDFs. So if it's a z-test, we use a normal CDF. If it's t-test, we do t-CDF. And because this is a chi-squared test, we're going to do a chi-squared CDF. And we're going to have a lower bound and upper bound and a degrees of freedom. Now, since our degrees of freedom is based on our categories, we calculate that by categories minus 1. Now, if we're going to interpret our p-value, this is how we interpret it. It is the probability of getting the chi-squared statistic if our null hypothesis is true. So if there's a low probability of getting that, then that means that we can reject HO. So we do that by comparing the p-value to the significance level. If it is less than alpha, so I would take my p-value and I check to see if it is less than alpha. If it is, I reject. If my p-value is not less than alpha, and that's what I do, I always use the same symbol so I don't get confused, and I check. Is it less? Then I reject. If it's not less, then I fail to reject. Now we interpret those in context. So if I reject, we have convincing evidence of HA. I have to state what that means. If we fail to reject, we do not have convincing evidence of HA. I don't actually write HA. I write down what that means in context of my problem. So let's go ahead and work through one so you get an idea of what this looks like. So according to the 2000 census, all of U.S. residents aged 20 and older, 19.1% are in their 20s, 21.5% are in their 30s, 21.1% are in their 40s, 15.5% are in their 50s, and 22.8% are 60 and older. So this is what we're expecting to have happen. So this is information for our expected proportion. So my expected proportion is this, 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 this for each age group. So that's for our expected. And so we're going to use that down here for our large sample. Now what we actually found in our sample data, these are our observed amounts. And we're going to check and see if those observed amounts are really the same as our population or are they different. So do these data provide convincing evidence that the age distribution of people who answer landline telephone surveys is not the same as the age distribution of all U.S. residents? So we're going to go ahead, and I typed out a lot of stuff for you so you don't have to write as much. We will perform a chi-squared goodness of fit test at the, well, let's go ahead, 0.05 significance level. So don't forget that's our alpha. And our null hypothesis is that P2, this is the proportion of people in the 20s, is 0.191. Where am I getting that from? This up here. So the proportion of people in their 30s should be 0.215. The proportion of people in their 40s should be 0.211. The proportion of people in their 50s is 0.155. And the proportion of people in their 60s or older is 0.228. So we're getting that up there from all that stuff that's highlighted in green. So this comes from all that green information up there. Now our alternative hypothesis is that at least one of those is incorrect. Now I have to state what PI means. What are these P's standing for? What does P2 stand for? P3, P4? So PI is the true proportion of people in their 20s, 30s, 40s, 50s, and 60s. So we're just letting people know, how are we labeling our information? Where is this coming from? So now we're going to go down to check our conditions. There's one thing I forgot to say. We're going to perform a chi-squared goodness of fit test. And that has to be in there. You have to tell what type of test you're using. So now we're going to go ahead and check our conditions. The table shows for a sample, so we had a simple random sample of how many U.S. residents. So looks like a total of 1,048 U.S. residents. +20 years old. Okay, large sample. So now we're going to the pink. Not the pink, the green, sorry. So this is our proportions, right? This is what we expect to have happen. We expect it to match the census, and we want to see, does it really match the census or not? So I'm going to take the proportion for people in the 20s, 0.191, and I'm going to times by the total of my sample, 1048. And that'll tell me how many I expect to be in their 20s. So when I calculate that, I'm going to find that I expect 200.168 people. And again, it's okay if it's decimals, because this, again, is just an expected value based on the percentage. And I just have to check, is that greater than or equal to 5? Which I'm good. So now I'm going to move on to the next sample, which is people in the 30s. 0.215. So how many of those 1,048 would that be? And I expect that to be 225.32, which again is greater than or equal to 5, so I'm good there. And I need these numbers because I need those numbers to calculate my chi-squared. So it's good that I'm calculating them right now. So now I'm going to move on to people in the 40s. So 0.211 times 1048. And that's going to give me 221.128, which is greater than or equal to 5. So I'm good. And then I move on to the next one, 0.155 times 1048, which gives me 162.44, which again is greater than or equal to 5. And I move on to the next one, 0.228 times 1048, which gives me 238.944, which is greater than or equal to 5. So I double checked all of them, and we are good. So now I have to check independence. So let's see that we did not sample without replacement, so it's reasonable to assume more than 1048, add a 0 on. People in US 20 plus years old. Okay, so now we're ready to calculate our chi-squared statistic. So for our chi-squared, we're going to go ahead and we're going to take the observed amount for the 20s, so 141. I'm going to subtract the expected amount, 200.168. I'm going to square that and divide by the expected. And then I'm going to do the same thing for each one of those. So now I'm going to go to 186. I'm going to go ahead and subtract my expected amount, which is why we list those out in those large samples, minus 225.32 squared, and then I divide by the 225.32. And then all I have to do is list out those. So now the question is how do I do this on my calculator so I can figure it out? So let me run over to my calculator. So what I have here is I have my calculator. I went to my stat. I'm going to edit my lists. And in my first list, I have those observed values. In my second list, I have all of those expected values. So now what I'm going to do is I'm going to calculate chi-squared. So I'm going to go up to that L3, and then you can see down here I'm going to type in some stuff. And I'm going to type in a formula. I'm going to go parentheses. I want to take my first list, which is my observed. And if you need to find the L1s, L2s, you just hit second 1 for L1, second 2 for L2. I'm going to do L1 minus L2 squared, and then I'm going to divide by those expected values L2. And that tells me all of those values right there. And so what do I really want for chi-squared is I want to add them up. Do I have to add them up by hand? Oh no. Our calculator has a nice function that allows us to do this. So we're now going to, remember this is my list 3, I'm going to go to stat. I'm going to calculate one variable stats for list 3. Hey, list 3 is right there. If you don't have list 3, you hit second 3, it pops up. We go down, we hit calculate, and this is the number you want. You want the summation. So remember, in our calculator, we had that E, or the sigma x. And so this is adding up all of those x values in list 3. So 223.867. Did I do something wrong? Hold on for a second. Okay, so I'm going to show you what I did wrong, what I figured out. And this is one of the things that bothers me about the old color calculator. So this is that thick, older calculator. And that is that I entered in 224 here, but if you enter the same number twice too quickly in these old ones, they don't work, which is why they came out with a newer, thinner one that has a better processor. So now I have to come back over here. I'm going to have to recalculate, so I'm going to have to do parentheses L1 minus L2 squared divided by L2. And yeah, now look at that. That is much, much better. So now I'm going to go back to stat. I'm going to calculate the one variable stats for list 3. And there we go. I thought that number was way too high with the 200. So we've got the 48.17197. So we're going to come back over here, and I'm going to show you moving back and forth between my desk. So, what was that number? 48.17. So our chi-squared is 48.17. So now we're going to calculate that probability. So the probability of getting a chi-squared greater than 48.17. So now we're going to do the chi-squared CDF. CDFs are always what we use for probability values. And we're going to have a lower bound of our chi-squared value. And that's always going to happen. Our upper bound is going to be something just really, really big. And so I'm going to go ahead and go 1 with lots of zeros. And then our degrees of freedom. So this is what always throws people because we want to take our sample size and minus 1. But with chi-squared, it's not like that. It's how many categories. So 1, 2, 3, 4, 5 categories, and then I minus 1. So my degrees of freedom is actually 4. And that will calculate that. So let's figure out on our calculator where that actually is. So let's go back here. Ooh, my screen's starting to go dark. Okay, so I cleared out that. I'm now going to go to the distribution menu, so second vars, and we're going to arrow down and see there's the chi-squared PDF. We're doing chi-squared CDF. So we're now going to use that 48.17, I think that was. Something just really, really big for the upper. Degrees of freedom was 4, I believe. And then paste. And so now we hit enter and we get our probability value. So I kind of want to talk about this probability value. You see that E negative 10, and I always get this over and over. What does that E mean? And it's really just a scientific notation the calculators are programmed with. So this is I'm going to just use 8.7 times 10 to the negative 10th power, which means that it's really 0 point, and then I'm going to have 9 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 7. Now, here's the other part that a lot of people do is they forget to compare it to our significance level. So is this less than our significance level of 0.05? If it is, we reject. If it's not, we draw a line through that symbol and we say we fail to reject. So since our p-value is less than 0.05, we reject HO. And we do have convincing evidence that at least one of the proportions for people in their 20s, 30s, 40s, and 50s, and 60s plus answering landline telephone surveys is not the same as the age distribution of U.S. residents. So that's what we're going to be working on. In fact, I've got a really cool activity for you for 11.1b, where we'll do our own chi-squared test.